Welcome back to the channel with practice problems for professional actuarial exams. You have some websites here with information about me and resources I provide for studying for actuarial exams. I direct the actuarial program at Illinois State University, and the information about it can be found at this site, smarturl.it/actuary. Illinois State University is a center of actuarial excellence. From the very beginning of this designation, from 2009, it was one of the first 9 centers of actuarial excellence in the United States and the first one in the state of Illinois. And if you would like to support our students and make a tax-deductible donation to our program, go to smarturl.it/ISU actuary donate. So here is our problem for today. It's from November 2012 course MLC examination. You are evaluating the financial strength of companies based on the following multiple state model. There are 3 states, 0, 1, and 2. I call state of being solvent, state of being bankrupt, and state of being liquidated. As you can see, you can only transition into liquidated but not out of it, so it's an absorbing state. States 0 and 1, I work this way that you can go from one to the other and back. For each company, you assume the following constant transition intensities. Going from 0 to 1, the intensity is 0.02. Going from 1 to 0, the intensity is 0.06. Going from 1 to 2, it's 0.10. Using Kolmogorov forward equations with step of 1/2, 0.5, calculate the probability that the company currently bankrupt will be solvent at the end of 1 year. Now, of course, note that this is a continuous process that we're working with. So we're going to have to work with the possibility of transition any time during the year, not just going from the beginning to the end. It's not discrete, it's continuous. And the additional difficulty lies in the fact that you can go from state 0 to state 1 and back. So you can transition there and back and there and back almost as many times as you want. And the problem does not clearly say this, but you're expected to infer from the words with step h equal to 1/2 that you will be using the Eulers method approximation of solutions of differential equations. Yes, indeed, that's what the problem says. I call this the original intent theory of actuarial examinations. I think it's a pretty funny joke, but think about it. So what does this mean? That you are expected to answer the question that the examiners intended to ask, not the one that they actually asked. You always have to be on the lookout for these key words that tell you what they intended. This with step h equals to 1/2. Why in the world would there be any step in a continuous process? Well, because you're approximating using the Eulers method approximation. So what is that Eulers method? Differential equations are always about working with a derivative of some type. You have a derivative of a function in some type of equation, find the function. That's the idea. And here is a very simple idea from Euler. Well, it's hard to work with a derivative. Replace it with a difference quotient, because the limit of f of x plus h minus f of x divided by h, if you let that h go to 0, that converges to f prime of x. So Euler says take a small value of x and just assume that the derivative is approximately equal to f of x plus h minus f of x over h. That's the core idea of Euler's method. As you can see, it's quite simple, nothing deadly about it. That's what we're going to do in this solution. So, okay, now you know that you will be using this Euler's method approximation. And we are given the forces. When we are not given the specific values, they're 0 because we know, for example, that mu02 is 0 because you can't get out of, you can't go from 0 to 2. You have to be first in bankruptcy to be liquidated. and 2, 0 is the probability of going from 2 to 0 is 0, and 2, 1, mu 2, 1 is 0 as well. And then mu upper 0, which is the sum of mu 0, 1 and mu 0, 2, this is the force of going out of state 0, is 0.02, mu 1 is 0.16, and mu 2 is 0. Mu 2 is 0 because state 2 is absorbing. This tells us that the generator matrix, which is the matrix consisting of these forces that we just calculated in this form, is equal to what you see there, minus 0.02, 0.02, 0, 0.06, minus 0.16, 0.1, and then zeros at the bottom because state 2 is absorbing. One very important thing is that I'm going to use the Kolmogorov-Forward equation in its matrix form. And I don't think the textbook on the exam gives you that, but you're supposed to really, well, you're supposed to. Not officially, you can memorize the formulas that are in the textbook, but I'm telling you, you should know the Kolmogorov-Forward equation in matrix form. Otherwise, I just cannot imagine that you can memorize all these formulas. I look at these formulas and I think, well, they can't possibly expect us to memorize them. But that, of course, is wrong. Every time you see a formula and you think, oh my God, they can't possibly expect us to memorize them, that's a very clear message to you that they expect you to memorize them. Don't ever dare thinking that you're not supposed to memorize things for actuarial exams. Yes, you memorize, and ginkgo biloba supposedly helps, but whatever it takes, you must memorize. Must memorize. You have 5 minutes per problem. So this is the generator matrix. And the transition matrix, the standard form, of course, it's a continuous model, but still it's pretty straightforward. Okay, so this is the Kolmogorov-Forward equation in matrix form. The left-hand side is the matrix of derivatives of the probabilities in the transition matrix. Pretty straightforward. And the right-hand side is the transition matrix times the generator matrix. Again, pretty straightforward. So you need to multiply these two matrices. And indeed, the question only asks about one of these probabilities, so it looks like we're going to work with only one of those differential equations. Well, lo and behold, because you're doing two steps, not one, you're going to end up with two of them. And yes, if you guess which ones and you do this only for those two, you will be faster. But I cannot imagine you'll be fast enough to do this problem in 5 minutes. This was a very challenging problem, and it's very important to know it. So to understand it, what goes on, because it doesn't get any harder than this, in my humble opinion. So you see, you have these, you multiply the two matrices, you get the matrix that consists of these terms, and the left-hand side are the derivatives, so there is 9 equations in here. But we are looking for an approximate value of the probability 1p011. We can actually remove the notation related to the starting point in time because due to constant intensities of transition, the starting time does not affect probabilities. And this is just like constant force and exponential distribution, or constant hazard rate for exponential distribution. The starting time does not matter for future mortality if you have constant force. That's the same phenomenon here. So the equation, that is one of those 9 equations that has 1 0 in it, looks like this, and that gives us an approximation that if we go backwards from 1 to 0.5, and the step from 1 to 0.5 is of length 0.5, and we have this difference quotient, that tells us that the derivative at 0.5 can be approximated this way, but the derivative at 0.5 is given by the Kolmogorov-Forward equation as the right-hand side. So we're actually going forward from 0.5 to 1, but we start out with the probability 1p10, so that's why I said going backwards from 1. We're using the equation approximation at 0.5. So the left-hand side is like f of x plus h minus f of x divided by h, and x is 0.5, and we looking at the derivative of this probability. Now we multiply through by 0.5 and also move the 0.510 to the other side, and we end up with the equation that you see here, which will let us calculate the probability 1p10 if we have the right-hand side. Well, we don't have the right-hand side, but we can do the same thing again. We can go from 0 to 0.5 using the Kolmogorov-Ford equations for the two terms that are on the right-hand side of the equation that we just derived. So we do this. We have there P10 and P11, and we have the differential equations for both of them, and we use, again, the approximation first for the derivative at 0 of P10, and then for the derivative at 0 of P11. And these are we're using two of the 9 Kolmogorov-Ford equations that we derived. So we multiply through by 0.5, combine the like terms, and we get these two equations. And now the things that show up in them are only P10 and P11 for the 0 step forward, so for not moving at all. Well, then if you're in state 1 and you have no time to move, you're not going to go to state 0, so the probability of going from 1 to 0 in 0 time is 0, while the probability of going from 1 to 1 in 0 time is 1. So we plug those values in, and we get the values of 0.5 P10 and 0.5 P11. We plug those to the first equation that we derived, and we get the approximation of 0.0573. That's answer D. That is what you were expected to do. So the wording of the problem, because it had Kolmogorov-Ford equation, which is a differential equation, and then it says use this step, it tells you that you're using a stepwise approximation of the derivative with a difference quotient, which is called the Eulers method, and you are expected to know this for the test. Please remember that this is copyrighted material. Good luck in your studies and good luck on the test. And of course, the problem comes from Society of Actuaries exam. So the problem itself belongs to the Society of Actuaries. The solution is mine. Again, good luck on the exam. Good luck in your studies.